Okay, good morning, everybody. Welcome to day 2 of this workshop, Active Learning for Material Science. And this morning, we continue with the active learning theme. Armi Tiihonen, Joachim Lökren, Matthias Stosik, myself, and Patrick, it seems we're presenting this morning's tutorial. But of course, Armi here is the lead. And her tutorial will be on Gaussian processes and Bayesian optimization. So a little bit more in technical detail about what Jörg was talking about yesterday. So, yes, thank you, Armi.
Thank you. Let's get started. So, here are some of the topics of today. So, yeah, after seeing yesterday how GPs and also active learning work in practice, so today we are going a bit more to the basics and principles. So we start by looking at some probability theory briefly, variance and Bayes theorem, and after that we take a look at Gaussian process regression. And then, well, this will be roughly the first half of the tutorial, and then we will move on to active learning, specifically Bayesian optimization. And we also look at some like different application examples of these methods. So here you can see how machine learning can be divided, like how methods can be divided. So we have like unsupervised learning, supervised learning, and active learning. And what this basically means is that in the unsupervised version, we have a data set. We have the inputs X, but we don't know the outputs Y. And in the supervised learning, we have both X and Y. And in active learning parts, we either don't have the data set at all, or we have some of the data set, but we want to sample more points. And yeah, today we are going to take a look at Gaussian process regression and Bayesian optimization. That's an active learning technique. And this is what you learned already yesterday. So on the left, you have an example of GP regression model. So basically you have the prediction of the function value, but you also have the uncertainty. And on the right, you have an example of Bayesian optimization. So there the focus is choosing where to sample next. And typically you want to optimize the also at the same time the function value. So basically what should be the next point to try if you want to find the minimum value of the function, for example, in the least number of tries. So yes, let's start with the probabilities. You are probably all quite familiar with these, so this is just a quick recap. So yeah, if we have a probability for event X to occur, it's basically this roll of dice probability. So for example, the probability of rolling number 3 is 1/6 for a die. And these probabilities sum up to 1. And yeah, as a recap, there's also the conditional probability. That means that what's the probability of event X given that event Y has already happened or is true. Yeah, and then there's also a joint probability. This p x comma y, that's for both events to occur. And here's an example of how these probabilities work. So if we have two groups of materials, in the first group, we have oxides, and it consists of one metal and two semiconductor materials. And in group 2, we have carbides. That's one metal and three semiconductors. And we want to calculate the probability of or chance of randomly picking a semiconductor, given we have already a group 1 member, or we know that it's a group 1 member. It's quite clear, it's 2/3. Whereas the joint probability of choosing group 1 and a semiconductor from all these materials is 1/3. So that's the difference to remember. Yeah, and if we go to the Bayes theorem, simply put, it says that that our prior knowledge can be incorporated to affect the probability of an event. And well, it sounds quite simple, but it's actually quite important and quite nice. So if you are thinking about those rollings of dice, so what Bayes' theorem allows us to incorporate is that, for example, if we are playing with a friend, and the friend has a history of, for example, cheating you in the game, so we have a method of trying to incorporate that knowledge to our calculation of probability. So it's quite like in practice, that's quite an important addition or important theorem. Yes, and here's an example of Bayes' theorem. So let's think about those oxides and carbides again. Yeah, so if you are trying to, like, after preparing the paper, you are trying to understand that what's the probability that the two materials in the documented heterostructure are oxides. How can you use the following information? So you know that at least one of the materials is an oxide, and or if the first material in the heterostructure is an oxide. So all right, so we look at case 1. So we know that one of the materials is an oxide. So then we are looking at the conditional probability that yes, so we are looking at the conditional probability that we have two oxides. For some reason I don't remember this at all. Maybe I'm going past this example because somehow, yeah, sorry. Yes. So yeah, now we go from the Bayes theorem to the probabilistic regression. Yeah, I'm not really feeling that well.
Sit down, sit down.
Yeah. All right, so yeah. So let's continue with the. Thank you. Take it as.
You want to make a break, maybe? Yeah.
Yeah, maybe let's have a 5-minute break.
Yeah, that's right.
It's okay.
Is the coffee out there? So okay.
Yeah, okay, later, just go ahead. This is just for the rest of the tutorial. I mean, yeah, it's yes, I do, but it's still good. Okay. Do you want this chair here? That I'm not going to. Maybe we just get it's nice to have a couple. All right, let's have a new try. Hold on, because we need to get people. Yeah, I unmuted. Okay, and then let's get people back from the. Oh yeah. Yeah.
Sorry.
So let's continue with the session, and Armi is armed with chairs, so yeah.
So yeah, and perhaps I need to learn how to pace around. So that's what I can say. All right, so let's go to the probabilistic regression. So like we saw yesterday, the point is that we are not only wanting to see the like most likely prediction for the function, that's the like orange line here, but we are also interested in seeing what are the other possible functions that could fill in the data points, or that could fit together with the data that we are seeing. And for that reason, we want to design a model that has two outputs, and the mean and also the variance of the predictions. And if we want to figure out how should we design such a model, so we can think about the basic like probability theory and also normal distributions. So if we just pick, so at this point we are just looking at discrete values of x. So let's pick x here and set a normal distribution for the value y. And if we pick another point, y2, and we define also y2 as a normally distributed variable, we can set up a covariance matrix between those two variables. So basically we have the variance of those two variables.
You need to plug in here.
Yes.
Yeah, so variance of those two variables alone on the diagonal, and then we have the covariance of how they are connected together. And if those two variables are fully independent, then the covariance matrix will look like this here. And if you are looking at the distribution, the 2D Gaussian from the top, it looks like this. And if you make those two variables correlated, then the distribution becomes more and more skewed. And when we are sampling from the distribution, it's a 2D Gaussian. So we are getting values for both y1 and y2. And we can pick or sample the distribution multiple times. Now, if we fix, like we pick the sample and then we look at the value of y1, then we are still uncertain of the value of y2, but we have a distribution of the most likely values of 1, 2, y2. Now, if we extend this to a higher dimensional Gaussian, and we still have this y1 fixed, we basically generate this distribution of different kind of possible lines that can originate from y1. And the covariance matrix is also increasing at the same time. So now it's 6-dimensional. And for each one of these variables, we can describe them by their mean and variance. And here, if they all would have the same variance, then what we know from, like basically from our intuition, is that the variance or the uncertainty should decrease when we are getting closer to that y1 value that we have already looked at. Yes, all right. This all sounds good, but it's kind of difficult to operate that kind of covariance matrix. So we can. It's basically so you always have one line for each each point in x-axis for these discrete values of x, and it's difficult to calculate. So here we basically used our intuition of how we want to set up the problem to fix the values of the covariance or values in the covariance matrix. But we cannot really calculate the covariance in practice. So now we extend to the continuous values of x by introducing a kernel, and you already explored some examples of kernels yesterday, so there are many kernel options that you can pick. And the idea of the kernel is to basically introduce our knowledge on the x-axis to the model. And for example, here you have a Gaussian or radial basis function kernel. And here you have a length scale. So that's a fixed value, kind of hyperparameter of the model that we are building. And then you have a distance between 2 points, x, y, and xj. And basically what's happening here is that you're connecting those 2 points together so that they should correlate more if they are more close to each other. And here you have another hyperparameter, that's the variance. That's basically showing you how much the values of the function that you are building or the model that you are building, how much the y values should change with the fixed distance that you are traveling on the x-axis. All right, so yes, good.
Is the covariance the delta in the previous slide? Is delta there a Kronecker delta, or what is it?
Yeah.
Yeah, okay.
Yeah.
Makes sense.
Oh yeah, sorry. I forgot to mention that. So that's introducing noise to our model for the y values. So basically we are not assuming that we have fully accurate observations of the underlying function. Yes. So now that we have this kernel and we have some idea of, or we have a method of bringing our knowledge of the x-axis to the model, we have generalized to continuous variables. So basically we can model any point on the x-axis with this model. Yes. All right. And what we have defined at the same time is actually a Gaussian process. That's a collection of random variables, a finite number of them that have consistent Gaussian distributions. And here, the random variables, you could think that the random variables are like these y values here. So basically you have a really you can think of these computations, and this is not a mathematical way of saying it, but you can think of these computations of having these large kind of matrices that you're operating. All right. And Gaussian process is fully characterized by its mean and covariance that you are seeing here. And now we are giving the covariance through the kernel that we have defined. And yeah, this is probably like doesn't feel super practical at this point. So so I would like you to think about the kernel a bit more. So that we use the kernel, or we choose the kernel based on our based on what we think about the problem or the underlying function, how we think it should look, and the choice of the kernel affects what the model, this Gaussian process model, can fit to. So that's why the choice really matters. So here you can see samples of GPs, different kernels. So here you have the radial basis function kernel that you saw earlier. Here you have two other kernels, Mattern and exponential sine squared kernel. So these are samples from GPs that have different kernels. And then now I give you 1 minute to think of these 3 questions on the slides. So firstly, if we have this RBF kernel, so to what kind of problems would you choose rather Mattern kernel than RBF kernel? And then the next question would be that what kind of problems would you choose this exponential sine squared kernel instead of RBF kernel? And the third and final question would be that we have this modified RBF kernel here. So what has been the change? What do you think has been the change in the hyperparameters compared to this RBF kernel here? And you don't have to Google anything, or you can basically just look at these examples or samples from GPs with these different kernels and try to figure out what's important here. What would you choose? All right, and now I'm gonna be quiet for one minute. Let's try to do that.
Yes. That's very significant. Yeah.
Right. So do you have any thoughts about the Mattern kernel? So for what kind of problem would Mattern kernel be better than RBF? And yes?
You could define some kind of frequency about population of these kernels. I can explain about exponential sine. It's somehow the frequencies are the same in comparison with the others, or the amplitude of the waves.
In the Mattern or in the RBF, or do you mean to compare the RBF and Mattern?
RBF and exponential, but I cannot see any oscillation or something.
Yes, yes, that's very right. So these two kernels here, they indeed have like the functions resemble each other, and the length scales resemble each other in that sense, because they have like similar types of hyperparameter settings. And what's like what's making this, so basically the maternal kernel here has more rapid kind of changes, and that's because like it's been defined so that it can adjust to faster changes or this kind of smaller how to say
Length scales.
yes, smaller length scales. Yes, so that's indeed the main difference between these two kernels. So the answer that I'm looking for is super, like, it's really simple. So basically, well, this seems to have these finer shapes. So probably you want to choose the maternal kernel if you expect your problem to. You expect that your problem is not as smooth as what RBF kernel produces. And then when thinking about this exponential sine squared, what would you say? To what kind of problems it would be better than RBF? Oh, sorry, yes.
It would be periodic.
Yes, indeed. So, and if you're, what I'm trying to say here, that like the choice of the kernel matters, because if like for example here for the periodic case, if the kernel is consistent or fits together with your problem and basically your domain, then you will learn the model, or it can fit better. You can learn it faster or more easily. And then the final question. So what's if you think about the hyperparameter values of RBF and this modified RBF, what do you think has been the difference? What's the visual difference that you are seeing here? Larger variance.
Distribution of the data is wide.
Yes, it's exactly. So you have higher peaks and deeper valleys. So basically the variance of these samples is higher. If we go, if we go back a bit to look at the RBF kernel, I should have probably added the equations to that exercise, but basically parameter has been modified. So that's the difference between those two RBF kernels. All right. Now, if we get into actually using our Gaussian process, so we are using it for machine learning predictions. We can take these random variables and we can redefine them here now. So that y1 is our training point. So that's our existing data set that we are using for fitting our Gaussian process regression model. And then y2 are the points that we want to predict. So we still don't know what's their value. And now that we have a Gaussian process defined, we can combine that with Bayes' theorem. So we want to look at the look at the probability distribution of predictions y2 given the data y1. And in this case, our y1 and y2 are in a joint normal distribution. And we have or we can define or calculate easily the conditional probability of y2 given points y1. And this is how the joint distribution for y1 and y2 looks. So basically, we still have, so it's a normal distribution, and we have the mean values here for the train, and in this case, test or predicted, or data points to be predicted. So M1 and M2, and then we have an extended covariance matrix between the train and test data, or the points like train points and points to be predicted. And then now that we have a normal distribution, we can also quite easily calculate the conditional probability. So basically, I'm not going to show the derivation here, but you are basically modifying the conditional mean by this factor, and then you are also modifying the conditional covariance matrix. And what you can see here is that the new covariance or new variance will be smaller than the old one. So basically, now that we have, so compared to the situation when we wouldn't have those previously sampled or tested points, we are more certain on the predictions. Okay, and these are kind of these mean and covariance define our Gaussian process. So this is how we can sample from our Gaussian process model. And now we actually we can use our model to predict the mean and uncertainty of any points on the x-axis, and you can also use it for sampling sampling the Gaussian process. So basically, you are drawing these example functions from the GP. Does it make sense? Yes, good.
So what the different colors of the lines are standing for now?
Yeah, they are just different samples, so it's like there's no specific meaning apart from like the orange line. That's the predicted mean, so that's the most, like that's the average of all the or the most likely value. So for example, at this point of x-axis, this y value is the most likely, or the prediction mean value.
Sorry, but then your uncertainty should just be between those sample points. It shouldn't be. If these are all different samples to mimic your data.
Oh yeah. So
uncertainty should be within those lines only then.
yes. So what I'm trying to picture here is that you have those samples. So these are the train data, the blue dots. And then when I mean that you can draw samples from that GP, so then you are basically sampling along all the points that all the x values along the axis. And then when you are doing that, so you can kind of think that you have a really high dimensional Gaussian.
It's not
so then
necessary.
you have this one line.
It looks like that many times.
Yes.
Oh, I see. So
Yes.
artistic freedom gone wild.
Yes, yes.
But you can draw from the GP many different looking functions that are outside of the uncertainty range, but they're still drawn from the GP.
Okay, I don't know. Yeah, thank you.
Does it make sense?
It does.
Yes. Any other questions? So yeah, why we went through all this trouble of looking at those normal distributions and conditional probabilities and how they work. So one of the nice things with these Gaussian processes is that when you have those normal distributions there, you can calculate many properties more easily. So that makes the math more nice. Yeah, advantages of Gaussian process regression are indeed that it's kind of easy to compute based on probability theory. It's also like it's a nonlinear model because you have those kernels. So basically, you can encode special properties of the domain into the kernel. And one of the big major nice things is that you can get the quantification of uncertainties for the predictions, and it's also pretty like it's noise resistant because you have the variance assumed in the model. And like I said before, you have those multiple kernel choices, and for that reason, you can apply it to many different problems. And yeah, of course, you are also learning with the data. So the more data you have, the better regression values you get. So what I mean there is that if you have, for example, here on the right-hand side, you have like quite dense sampling there, so uncertainties are smaller than what you have in the middle. All right, these advantages of TBR are that it requires the matrix inversion. I forgot to mention it here. So, for example, here you have the matrix inversion. And yeah, so basically, if you have a really like large problem, then those operations become slow. Yes, and with the basic GB, it's easy to predict scalar quantities. But if you have, for example, vectors, it's not so easy. Yeah, and there's also the point of data representation. So like basically, if the model and data representation are not compatible with each other, the model is not learning as well. So you have to you should use some kind of domain knowledge here, or it's very beneficial to use it. So how can you use it, or how can you use Gaussian process regression in material science? So here's one example from this recent paper. So they basically wanted to investigate the fatigue of metallic materials, and they had an experimental data set of more than 300 fatigue experiments for 12 different metals. And they used as their input variables. So basically they had a 3D input that they retrieved, or retrieved from the stress testing of those or from the experiment. And then the output was this fatigue life of the sample. And they basically wanted to do predictions for different metals. And for this purpose, they actually tested. So these red points are actual measurement values. And then you have the predictions. Yes, you have the predictions on with the blue value. So they basically tested several different test materials and found out that and compared. So basically they fit regression models, several different kinds of regression models, and one of them was Gaussian process regression, and they found out that the mean absolute error of GPR was less than 4%, and it outperformed the other methods. So some of these other methods were kernel-rich regression, decision trees, neural networks. So basically, you can use Gaussian process regression for doing regression and making predictions, especially when you have data that has inherent noise there. Here's another application example from this paper here. And here the purpose of or the motivation for choosing Gaussian process regression was a bit different. So this is also related to materials. So they wanted to do structure analysis of plastics, and basically, so here are these circular points are the prediction mean, and then you have the I think yes. So you have the 95% confidence, like upper and lower boundary for the prediction. So you have, so they are predicting force versus displacement. And
yeah, sorry, but this is where actually I have a lot of problems. So when you use GPR, then your derivative is defined on every function. But such a system at the upper bound and lower bound, your derivative is not defined. How does that make? How can you use GP for such systems? Because, like mathematically, the derivative should not be defined at the lower bound and upper bound.
Yeah. So why would you? Okay, so you would like to get the derivative so that you can explore the like trust region. Is that the reason why you need it? Or?
My point with your prediction is always going to be wrong, especially at these edges. And we already know that because of this. So I don't understand how you could do how GPR could be the best. I would think same matter kernel would be better because it has a.
Yeah. So
versus matter.
Yeah, for example, I would just think RBF would be really bad for such a system.
Yeah. So the kernels have differences. You're right, and here I don't actually even remember which kernel they used here.
It's not clear if they use RBF.
No, but even Gaussian process, any GPR model, one of the criteria is the derivative should be defined on your sample space. But for such systems, we know for a fact it's not.
And why it is not defined here?
Because
Continue.
like if you look at the upper bound, the derivative is not defined.
It's just it's sampling maybe.
Yeah. So here you're exactly right. So I think that it is actually it's not really like a
It's just
phase
a curve
change
across. You don't see it. You just see the data point.
Yeah. All right. So so basically they were trying to predict the force versus, so basically they are bending plastic materials, and here they are actually using GPR because you get those uncertainty estimates. So they focused on the boundaries on those extremes, and basically models how the plastic sample would look or looks on the upper and lower boundaries, and that's how you can get. Sorry, I forgot to change the title. So you get better like stochastic analysis of how the plastic survives the loading. So basically I have shown two applications. So firstly, you can use TPR for regression when you think that, especially when you have variations in the samples, and here you are using TP for giving better estimates on those more unlikely or like more extreme boundaries. All right. And then just quickly about practical things. So there are several packages where Gaussian process regression has been implemented. So for example, it's in scikit-learn, GPY, GPFlow, and all of these are using slightly different notations and slightly different basic settings. So So for example, sometimes the package assumes that the data that you're feeding in is must have a zero mean. Sometimes the package doesn't assume that. So you need to check the check every package separately, or whichever you are using. Yes, and we already spoke about kernel choice. So that's where you are basically using your own domain knowledge of the problem. And then I would also like to point out that also for these Gaussian process regression problems, you have those hyperparameters there, and you should optimize them. So that's sometimes like it's integrated sometimes quite nicely to the model in the code implementations, and sometimes it's not so well integrated. How much do we have time for the
about 30 minutes.
Perhaps we can, let's continue directly. Yes. I was initially thinking or planning to have a small break here, but I guess that I arranged the break. Yeah. All right. So next we move on to active learning. And there we have this kind of learning or optimization targets. So for example, we want a maximum yield for some process or from some process, or we want to achieve lowest energy structure, for example, or high performance. And specifically in active learning, what's a big difference to the GP is that we can still collect, or like a big difference to regression assumption is that we can still collect new data. And this is quite close to, for example, design of experiments in statistics literature. So this is not like, or how to say this, this problem has been around like for a long time, and there are multiple solutions that are trying to that have been suggested for this problem. And this is the principle of active learning. So at first you have some data on the top, then you use or fit some kind of surrogate machine learning model to that data. And then you define some kind of acquisition strategy that for deciding which point you want to sample next. Yes, and here the data is assumed to come from a black box function, and that could be, for example, your experimental or computational like experiments. And the surrogate machine learning model could be, for example, the Gaussian process regression model that we just had a look at. And like I already said, the acquisition function is your strategy of deciding which points you should be evaluating next. And yeah, there's no definition of like how many iterations you can, so you can do infinitely many or as many iterations here as you want. But in practice, you probably want to stop at some point, and typically you do that. For example, when you have good enough results, or the search has somehow converged, and you estimate that okay, you are not going to get better results anymore. Or another possible criteria is that you have just met your experimental budget, so you just cannot afford sampling more. Bayesian optimization is the one version of active learning, and that's basically active learning that's acknowledging the Bayes theorem that we had a look at earlier. So basically, we are here saying that our prior knowledge or prior experiences can affect the optimum that we are trying to search. So it can affect our next sampling points. And BO is using probabilistic surrogate model. So most typically it's the Gaussian process regression, but it could also be some other model like random forest, anything that you can define as a probabilistic or treat as a probabilistic model. And in Bayesian optimization, you are not necessarily trying to learn the problem domain, or learn the best possible model describing the domain. You are actually trying to find the optimum value from the domain with least possible experiments. And yeah, for this reason, it's designed specifically for expensive samples. So when you cannot sample, or basically you have an experimental budget that you have to meet. Yeah, if we yeah, so if you think about this active learning cycle for Bayesian optimization, so for the data step, we could have, like I said, experimental or computational data, and in the typical implementation, it's quantitative data. You have kind of implementations also for example, categorical data, but it's not as straightforward. And here, one of the big differences is that like in regression, you already have the X data. So you cannot really so you have some undefined search space or like input space there. Here, you do not necessarily have any data when you are starting with, so you can basically design your search space. So you can decide your X variables and the range that you are searching, and you can also decide what you are actually trying to optimize. So so what I'm trying to say here is that your choices, like these choices, are really important for the success of the search. So as an example from my own work, if you have this ultimate target of trying to optimize or find find more stable perovskite materials. Like, how do you define stability? Like your ultimate target is stability, that's right, but what's the actual like variable that you are going to set here? Is it the let's say, is it some like peak amplitude in your XRD measurement after a certain time, or is it color of the sample after certain environmental stress? So it has to be something that has like that you can actually measure, and hopefully you should be able to measure it quite accurately, for example. And also for the X variables, if you are trying to find the perovskite material with optimum stability, what's like, you probably cannot explore all the possible perovskites out there. So you have to somehow design the or fix the composition range. And if you're trying to be in too much hurry in this phase, then you will probably like you might be like designing your search space X so that the optimum is not even there. Okay, now I get too excited. I'm so excited about this data part. Yes, and yeah, in the case when you don't have any data to start with, like for this active learning cycle in this upper corner, you need some data for the first round. So you can initiate that, for example, by random sampling. Okay, and then in the second step, you have the surrogate model. And that's like during BO, that's gonna improve round by round. So in the first rounds, the model is probably quite bad, and hopefully after you are converging, it's probably going to be quite good, at least near the optimum region. Yeah, and for the surrogate model, that could, for example, be the Gaussian process regression. So you have to do those choices that we discussed earlier. So you need to pick the kernel. The model has hyperparameters. That's like in many implementations of BO, they are optimized like more or less automatically during the cycles. But you need to also like think about those a bit. And here I'm again trying to show you some graphs. So here you have like a Gaussian process regression surrogate model from Bayesian optimization. It's an imaginary model. And here you have a ternary perovskite space. So you have Fa, Ma, and cesium lead pre-iodide material. And this is the mean value where like red color is high values, high mean values, and blue color is low mean values here. And this is the standard deviation of the model. So I'm gonna be quiet for 1 minute again, and you can think about what kind of things you can say from the previous Bayesian optimization cycle and the surrogate model and the samples used to train it based on this mean and standard deviation. So if you have some like observations.
So sorry, what was the color bar depicting?
Yeah, so
Value of
here this is like this is an imaginary model, so it's not really like anything specific here. And I have done a very similar like BO on perovskite stability, but this is not exactly that.
Yeah, so that's some random.
Yes, so you're trying to minimize something here. That's what's important. All right, so
If you want to speak, just raise your hand.
If you have no data points in the middle of your,
yes. Yes, excellent. That's right. How did you,
the standard deviation is very high,
yes.
so your model is not sure about.
Yes, excellent. Other observations? Well, you can probably also notice that these are the likely sampling points. So there in those points the uncertainty is lower. So if you're looking, yes,
Regular grid.
yes, exactly. Regular grid with one one gap. Yes, yes. So yeah, here are the actual samples on the left that you can see. Yeah, and something that I wanted to point out here is that if you are looking at, if you are only looking at the mean prediction of the surrogate model from Bayesian optimization, you can easily go wrong here because it's a result. So typically it's a result of somehow uneven sampling, because you are trying to do smart choices of sampling here, and in some cases it's not uniform sampling, or the model certainty varies over the domain, and basically you should never try to just take the surrogate model from BO and then analyze the mean prediction only, because it's not really it's basically a biased very predictive model of the domain. So always look at also the standard deviation, and well, preferably also the actual samples that have been used for preparing the model. If you think about the third stage acquisition, so there are multiple different strategies, and you tried at least 2 or 3 of them yesterday. So for Bayesian optimization, they all revolve around exploration and exploitation. So if you are exploiting the kind of model or samples that you already have, then you are sampling from regions that have already performed well in the past. So basically you are in the acquisition function, you are utilizing the mean prediction. And if you are doing exploration, then you want to go and sample in the regions that have not yet been sampled before. And here is one acquisition function, exploratory lower confidence bound acquisition function, and it has these mean and variance components there. So it's utilizing the mean and variance of the surrogate model that you have at that point. And for this acquisition function, you are choosing the next acquisition point by the mean of by the minimum of the acquisition function. Yes, and something to notice here is that in this ELCB function, you have the acquisition counter here. So it's basically doing, let me check, yes, it's doing more exploration when the search is progressing and less exploration at the beginning. For example, here is another, yeah, it's supposed to be expected improvements. Yes, so another acquisition function that's quite commonly used, and that's trying to balance. That's also trying to balance the exploration and exploitation. So it's basically minimizing the expectation value so that it's trying to choose points that are expected to be better than the previously sampled, or the previously found optimum. And here I don't have the these mean and variance components here, specifically out there, because the because the full equation is quite long. But you can also divide this acquisition function to the exploration and exploitation part. Yeah, and something that I was, for expected improvement, it's also good to notice that you have this previously sampled optimum here as a part of the acquisition function. So if you have very noisy data, this expected improvement is maybe not the ideal choice for those cases. Yes, and yeah, this is what I actually mentioned before. So you can how to decide when to stop this PO cycle is basically that you either meet your experimental budget that you have defined before, or you have sufficiently good optimum values. So you are happy with the result, or you are converged with your search. So you are not finding the optimum is not moving around in the search domain anymore. Here is a 1D example of PO. So there are many lines here. Let's go those through. So here you have with the black color, you have the true function. So the underlying or the ground truth. And here with the blue line, you have the mean prediction from the surrogate model. That's the Gaussian process regression. And you have also its uncertainty estimate, gray shaded area. And you have with the red color, the 3 points that have been sampled. And yeah, at this point, the model says that the minimum, so basically the minimum of the mean function is here with the green line. Yes. Right, and then we are sampling another point from the right-hand side of the graph. So the model mean, if you compare the uncertainty changes and also the model mean changes with this new data point. Also at the same time, the green line, so the prediction. Yes.
That's a trick.
We are prone for accidents today. Yes.
We are two.
Yeah. Yes.
Right. I have a question on the slide before. I mean, the 3 and 4 points. What kind of struck my eye was that the not even the uncertainty of the right-hand side changed, which makes sense. But what is strange to me is that when you go from 3 points to 4 points, also the left-hand side the uncertainty is pretty much lower.
Yes, and that's probably because the this surrogate model hyperparameters have changed when you have done the repeated, you have added the new data point and then you do the optimization again. So those have likely changed. So I interpreting this correctly? I think that the length scale has probably, length scale has increased. So that's the reason.
Thank you.
Yes, and basically this is how you are continuing. So here you are sampling 5 points, so you have less uncertainty, and after 9 points, the model is basically certain that it has found the correct solution. So that's how BO works. And if you think about the advantages of this approach for Bayesian optimization and also active learning in general, so you don't need to have the data in prior, and you can decide how to do it in a smart way, the data collection. And this is sample efficient, especially depends on how you design your acquisition function. So you can choose your acquisition function to meet with your basically your aims for the data collection. And this approach works also for little data or no data to start with. And you can use when you are using these probabilistic methods, you can also encode your prior information to the search, which is pretty nice. And these are these methods are nice for open-ended searches where you basically want to optimize something, but you still don't know, it's really unexplored and you still don't know how far you can get. These advantages are basically scalability. So for example, if you are using Gaussian process regression as the surrogate model, then its performance is decreasing at every iteration. So with large data, it's getting more and more slow. And also the acquisition function, basically, it's quite clear that you want to find the optimum of the acquisition function. But if you have a very high dimensional problem, how to find the optimum or how to pick the optimum of the acquisition function. And there's also the scalability topic. So you have these sequential iterations. So that's why it takes time to arrive to the result. And we already spoke about bias. So so the intention here is to bias the data collection, but you need to remember it when you are analyzing the result. And we spoke about the search space definition. So if you are defining the search space so that you cannot find the optimum that you are actually aiming for, so then the search is not going to work. And to show one application example here, it's about lignin extraction optimization. So lignin is it's a compound that you can get from wood. And when you are processing the wood, you would like to extract as much of that lignin material as possible. What's lignin? It's something that gives mechanical strength to plants, so the trees can stand up. And it's currently not really utilized in wood processing, but one of the intentions is to try to start using it more. Okay, and here this is in this paper. This is Joachim Löfgren's paper, and he is actually going to speak about this topic later in the week in his talk. Yeah, so in this previous paper, the idea was to use active learning and specifically Bayesian optimization for optimizing the lignin yield. So you are modifying lignin extraction conditions to get as much lignin as possible. So basically, in this example, you had these experimental variables, and you found the optimum point where you are getting the maximum yield by sampling only 20 data points. So basically, you get the optimum faster, and you get also these like nice correlation maps that make it easier to understand the domain. Yes, okay, good. Yeah, and about practical topics. So there are also multiple packages for Bayesian optimization in Python alone. Today in the exercise, you are going to get to use one of them, BOSS. That's developed here by Patrick and Milica and all the other developers that we have also here in this workshop. Yeah, I think I actually mentioned basically all of these topics already. So you need to think about how you choose the surrogate model and what's a reasonable acquisition function in your application. And here it's good to also think about what's the noise level of your data, if it's computational or experiments, what's happening there, what's the true dimensionality, what are the practical dimensions that you can or are able to explore if you have those special properties like periodicity, and if your noise, for example, is isotropic or not over the domain. So basically you need to design well before you start implementing. You can also do like single sample acquisitions or batch acquisitions. Yeah, and the final point is that here in active learning, you are doing this iterative cycle, and you may have like, this is designed for expensive sampling. So for example, your experiment may take a long time or your computation may take a long time. And you are running this BO, whatever code you have, you are running it multiple times. So it's nice to have a smooth user interface, like so that you can actually feed in new data. Because otherwise you are going to forget on the way that, okay, which settings you were using and whatever. So something to keep in mind. Yeah, finally, a few words about BOSS that you're going to test later on today or after the break. So it's a Bayesian optimization structure search Python package, and it's designed for the global exploration of base spaces and also for accelerated determination of structures. And it can like accommodate, or it's good at accommodating both computed and experimental data. So for example, the lignin example that I mentioned earlier was implemented with BOSS. There are two interfaces. So there's the Python API and also the command line interface. And there are multiple like technical features that support the integration of BOSS with computational codes, for example, DFT. So you can, for example, quite easily resume and restart your Bayesian optimization And there's like properties like the search of minimum energy paths and global minima tracking and local minima search. I forgot to, sorry, I should have a video here.
It was playing.
Oh, it was playing. Okay, good, good. Yeah, yeah. Some reason it wasn't like it was. Yeah, yeah. Okay. Yeah, so this is one of the examples where you can use BOSS. So there was like in this Yaris paper, the aim was to search for the minimum energy orientation of CAN4. So what you saw here was how the minimum energy orientation was varying when the Bayesian optimization cycles went on. So sometimes what you saw there and what I was aiming for showing is that like sometimes the minimum stays in place for a bit longer time and then it's not moving, and sometimes then you go into the phase where it's moving a lot, and the optimum is actually moving. All right, so you can use BOSS for this kind of searches, and yeah, it also has the like the Bayesian optimization functionality implemented. So you have the Bayesian optimization algorithm there, and you have Gaussian processes that you can use as surrogate models. You have n-dimensional kernels, and you can also set priors for the hyperparameters for the searches. Okay. Yes, I wanted to also mention that that we are developing BOSS constantly. So there are these new like features coming, multi-fidelity and multi-objective. So they are coming quite soon, and we have just implemented symmetries and gradients, gradient utilization. That's something that you can also test in tutorials. Am I? Yeah. Yeah. Okay.
You're finishing up, so just
Yeah. Good. All right. So
you can finish if you want.
yes.
To slide.
Okay. Good. Yeah. So we are continuously developing BOSS packets. So so feel free to try it, and also the new features. Yes. So just as a really quick recap, so we have Bayes' theorem saying that prior knowledge can affect the probability of an event, and Gaussian process regression is using that, and also Bayesian optimization is using the same principle, and you will get to test both of these after the break.
Thank you, Armi.
Sorry.
Questions that you want to ask now? Yeah.
Maybe one thing I was thinking, like, as you were showing that at some point you are adding to the kernel also the noise. How would I make or think of it in the terms of this one-dimensional diagram and this line? Because then all the points were they were exact, let's say. But now we have in some things we have any kind of noise, so it's like all of these. We have the uncertainty that is there, plus there is like a noise in every other point.
Yes, yes. So if you would have like noise there, then you would see like the uncertainty of at the point of observation wouldn't be zero exactly. Yeah.
So this is your true function and this is your data point and this is your noise on the data point. Then the model could kind of pass through here or pass through here. Doesn't have to pass through here. Right? That's the whole point of it. It's just that often you don't see it on these graphs because the noise is like 10 to the minus 1, 10 to the minus 2, right? So on the scale of what is y, you don't really see it, but that's what's really happening.
Yeah, so
Okay.
there's like two sources of variances. So there was the like this kind of variance, and then there's the it's all right, uncertainty between the samples that's a lot higher.
Okay, thank you.
Excellent question. Noise is often an overlooked
Yeah.
subject in Bayesian optimization, but it's really, really important to kind of treat the samples correctly.
We have time for one more question. For these kernel choices, if it's analytical, why can't I just add the different kernel functions and allow the machine to like a linear additions, and then just allow the
You can
machine?
modify the kernels. You can do that.
So then why do we have to worry about the choice? Why can't we just linearly add all of it?
And all of them. I guess that there the problem is that you are introducing more and more hyperparameters there. So then it's kind of you need more and more data to get to the same like accuracy of the model.
It's I mean, it doesn't become more computationally expensive, because if it was say smooth, it would automatically just go towards the
Yeah,
RPF and become zero every
yeah,
time.
it's not really computationally, or well, apart from the fact that you have to optimize them somehow, but it's just that the model cannot be as good. Yes.
I think it would be better. No comment.
So not only, so it's you want to avoid adding too many hyperparameters. Not only will you, it is computationally more expensive, but you run the risk of not finding the correct solution. The more hyperparameters, the larger your search space, like multiple dimensions.
Yeah.
And then you'll find a solution, but whether this will be an optimal fit for your Gaussian process to your data, that's no longer certain. So when we have the smaller number of hyperparameters, then we are at the same amount of computational complexity, somehow guaranteeing a good fit.
And they are like machine learning is never basically kind of a magic bullet where you can just feed in your data and be happy if it's something, but you have to do these choices with all the models. And I would also say that probably it's better to have that kind of model that has multiple kernels than something that has a completely wrong kernel, but neither one is actually what you want. You don't want a completely wrong kernel, and you don't want that kind of sub-ideal kernel, but you want a good one in the end.
Yeah, I think we can stop for now. And if you have any further questions, you can come and ask Armi. And now we have a coffee break until,
Let's meet back here at 11. So
yeah,
30
11.
minutes.
Okay, thank you again.